Good morning or good afternoon, depending on which Algebra 2 section you are in. This is the video for the lesson for August 21st, 2020. Title of the lesson is Properties of Real Numbers. I will try to upload a scanned copy team site so that you are able to access those either before or after the lesson to help you just follow along with what we're doing. This first lesson should be fairly short, and what the plan is for me to do about a 30-minute video lesson where I take you through the concepts. We might pause it in a couple places for you to do some practice work, and then our next class period will be going over the homework assignment and reinforcing these ideas from this first. So what we're going to talk about are real numbers. And if you haven't done Algebra 2 at any point before, you might be thinking, well, like a real number as opposed to what? Like what kind of a number wouldn't be a real number here? And so we want to define what a real number is. So first thing that we have, good grief, is the definition of a real number. Now, it's actually a pretty complicated definition, but I'm going to keep it really simple for you. A real number is any number on the number line. So if you can find it on the number line, if it exists somewhere on the number line, it is a real number. So just for a moment, let's take a look at the number line. So we have the number line, we have the number 0. Right in the middle of it, we have positive numbers over to the right, we have negative numbers to the left. That means that all positive numbers and all negative numbers are real numbers that like you can think of. So we have like the number 1, the number 2, -1, -2, and so forth. These would all be real numbers. Now, 1.5 would be located exactly halfway between 1 and 2, so that would make 1.5 a real number. That is a 5. It's a terrible 5, but see if I can do it. So that's 1.5. So that would be a real number. Fractions would be real numbers. So if I come over here and I have -1/2, okay, that would be halfway between -1 and 0. That would also be a real number. Now, other numbers that you might think of, well, like what about pi? Okay, so pi is what's called an irrational number, and we're going to talk about what the definition of that is. But pi is approximated by 3.14. That's typically the approximation we use. And while it might be difficult to find it exactly on the number line, I know that it's there. It's somewhere between the 3 and the 4. Okay, so it's somewhere between the 3 and the 4 over here. Exactly if I have my like little red dot in the exact right spot, like that I don't know. So a real number is any number on the number line. Prior to Algebra 2, you have not seen any numbers that are not real. So pretty much any number that you can think of is a real number. In this course, we will talk about numbers that are not real. Those are called complex or imaginary numbers. So what we're going to put together here is a kind of Venn diagram. And I'd like you to write this down in your notebook to copy it down. This big box that I've drawn here, we're going to call that the real numbers. So all of our real numbers are in here somewhere. The real numbers split into 2 sections. And I drew that a little bit off center because one of these sections is actually bigger than the other, although we're going to have more stuff in the smaller section, but this is actually the bigger set of numbers. This set of numbers over here are what we call irrational numbers. Okay, and irrational numbers cannot be written as a fraction. Or you might think of them as numbers or decimals that never end and never repeat. So I'm going to come over here and give us a definition. Irrational numbers cannot be written as a fraction. There's no possible way to do it. One way you can remember that is remember fraction and think ratio. Inside the word irrational, prefix "ir" means not, and so you have not ratio or not a ratio or not a fraction. They cannot be written as fractions. So what are some examples? Easiest examples to come up with are your square roots. Most of your square roots are irrational numbers. The exception would be something like the square root of 9, which is 3. That is rational. But square root of 2, square root of 5, square root of 6, square root of 7, square root of 8, like all of those would be irrational. I mentioned this one a few moments ago, pi. But we want to get like the idea that there's actually a lot more of these numbers. So I'm going to give you this one number here, 1.1211211121111 and ... Okay, you get the idea there. An irrational number is a number that cannot be written as a fraction. You might also see this definition of an irrational number. It is a decimal that never ends and never repeats. Okay, it's a non-repeating, non-terminating decimal. Terminate means to end. So if I go back and I look at this, there is a pattern here. So what I don't want you to do is think of like irrational means there's no pattern. There's definitely a pattern here. We have 1 1 followed by a 2, then 2 1s followed by a 2, then 3 1s followed. Definitely a pattern, but that pattern will never repeat itself because we will always be changing up the number of ones, and it never ends because you can always put in another 1 into your pattern. So this would also be an irrational number. Proving that a number is irrational, meaning that there's no way that you could write it as a fraction, is typically a college level problem. Now, on the other side of this, we have what are called the rational numbers. So we have irrational for not rational and rational. Kind of makes sense. And it's one or the other. A real number is one or the other. It's either rational or it's not rational. These are what we would call mutually exclusive sets. Like it's one or the other, and it has to be either one or the other. The symbol for the rational numbers is this. It's like a funky looking Q. A Q with a little bar in it. And the reason for that is if you think to ratio, a ratio would be something like 1 to 2, and we might also think of that as a quotient, the quotient of 1 and 2, and so we have the Q for the symbol for the rational numbers. Rational numbers will give us a definition over here. Rational numbers are numbers that can be written as fractions. Or you could think of it as decimals that repeat or terminate. It doesn't mean that they are written as fractions. It just means that they can be. So 0.5 is not written as a fraction, but I could write it as a fraction. -4 is not written as a fraction, but I could write it as -8/2. It's possible for me to write them as fractions. So that's what your rational numbers are, any number that can be written as a fraction. Now, inside the rational numbers, we're going to have several other sets. This set here is what's called the integers. And the symbol for the integers is a Z, a funny looking Z. I had a student ask me like years ago why the symbol was a Z, and I had to look it up because I didn't know. I just kind of took it for granted that the symbol was a Z. It has to do with the German word for integer. The German word for integer starts with the letter Z, and so it was a German mathematician that coined the term, and so it's a symbol as a Z. The integers, these are like what I call the friendly numbers. These are the numbers that you like to see as the answers to your problems. You like to see integers in your problems. And the integers are better just defined by showing you an example. The integers are the positive and negative whole numbers. I don't know why I did the 3 on one side and not the other. That's going to bother me. Hold up. There we go. I have to make it symmetrical or I'll be unhappy. So those are your integers. As long as you get an integer for an answer, most of you are pretty confident that you've done it right. When you get other kinds of numbers, like the square root of 2, or you get fractions, that's when students start to panic a little bit. I call them the friendly numbers. Now, inside the integers, we actually have 2 more sets we're going to look at. This set, the orange one here, is the set of whole numbers. And then inside the whole numbers, we are going to have what are called the natural numbers. And I don't know if I'm going to be able to fit that in there. Oh, I can. The natural numbers. So these are all what we would call subsets. Any whole number is also an integer, any integer is also rational, and any rational number is also real. So we have these like kind of nested subsets. The difference between a whole number and a natural number, I always forget this. I teach it at the beginning of college algebra and the beginning of algebra 2, and then I don't think about it again for another year. The whole numbers are simply your positive integers including 0, and your natural numbers don't include the 0. Okay, and so you can tell if a number is on this list, then it's automatically on this list, which makes it automatically in this list, which makes it automatically in your rationals. So you have those nested subsets there. In terms of what's really important for you to know for this class, you do want to know what a real number is. You want to know that real numbers are on the number line somewhere. You want to know the difference between irrational and rational. So irrational are numbers that cannot be written as a fraction, or you can think of it as a decimal that never ends and never repeats. And a rational number can be written as a fraction, whether or not it is. You also want to be familiar with the integers, just the definition of that. Think of them as the nice numbers and the friendly numbers. So that's what you need to know in terms of like crucial vocabulary when we're talking about basic sets of numbers. And hopefully none of this is super new for you. All right, so let's move on. In this section, this very first lesson, we also have comparing numbers. And it would help if I had the pen active. All right, so comparing numbers. When you're asked to compare in math class, what you're being asked for is this: less than or equal to, greater than or equal to. Sometimes just straight not equal to, but that's not what we're talking about here. I'll just throw it out there just so that you know it's kind of under the umbrella. Unlike an English class where comparing and contrasting means something totally different. So if you're asked to compare numbers in math class, you're just asked like which one's greater. The easiest way to do that is to change the number to decimals. That is the easiest, most straightforward way to compare numbers. So for example, if you had to compare the square root of 17 to 4.234. Right, so let's talk about this for a moment. I'm going to do a little bit of scratch work here. The square root of 16, I hope you know, is 4. So it stands to reason that the square root of 17 is going to be a little bit greater than 4, because 17 is greater than 16, so the square root of 17 would be a little bit bigger than the square root of 16. Now, whether or not it's that much greater stands to be determined. Like that we don't actually know. So the easiest way to do this is to whip out your calculator, actually do the square root of 17, change it over to a decimal, and once you do that, hopefully you can see which number is bigger. Now remember your inequality symbols, it always points to the smaller one and opens to the bigger one, so you use the analogy of an alligator, whatever. So we would say 4.123 is less than 4.234. This symbol and this symbol, they're the exact same symbol, they're just flipped differently, and so if you're reading from left to right, you're going to read it less than here. And if you're reading from left to right, you would read it greater than, but it's really just the same symbol. So let's take a break for a moment. And if we're in class, we're going to pause the video at this point, so you can do this in your notebook. And if we're doing this virtually, I'm going to pause the video and let you do it as well. I would like you to compare 3 over 2 to the square root of 2. Okay, and the best way to do this, again, is to change them over to decimals. That's just the most straightforward way. We don't want to do extra work. So 3 over 2 on your calculator, you would do that as 3 divided by 2, which would give you 1.5. You do the square root of 2. In your calculator, we get 3.414. The number on the left is bigger, and so we open it to the left, and when we read it from left to right, because it's oriented this way, we'd say 1.5 is greater than 1.414. Or if you want to go back to the original phrasing of the problem, you would say 3/2 is greater than the square root of 2. Now, if you are not getting that correct, okay, or this for that matter, so you whipped out your calculator, you did it out, and you got some other number, I need you to send me a remind. Or if we're doing this virtually, I want you to, first chance you get, comment in the help center and tag me in it so that we can work it out. That's probably a calculator issue where you're not hitting the keys in the right order, and it's easy to fix, but we can't fix it unless I know you need to fix it. All right, some vocab. Everybody likes vocab. Actually, nobody likes vocab, but it's very important. So we're going to go through some key vocab here. One is the word opposite in math class. Now, I am going to throw this one out. The other term for this is additive inverse. Okay, the word inverse comes up a lot in math, and you'll see why in a bit. Opposite means something very specific in math, okay? And people will use the word opposite when that's not exactly what they mean. So in math, when we say the word opposite, this is what we mean. We mean we add them to get 0, which is what's called the additive identity. So examples of opposites would be 3 and -3, because 3 plus -3 gives you 0. Or -11 and +11, because -11 plus 11 gives you 0, and it works for fractions too. So -1/2 and +1/2. So these are the numbers that when you add them, you get 0. So when we use the word opposite, what we mean is the opposite sign. Like the opposite of a positive is a negative, and the opposite of a negative is a positive. Now the other term that goes along with that is reciprocals, and the other word for that is the multiplicative inverse, but I prefer reciprocals. Well, what in heaven's name is that? Hang on. Reciprocals. There we go. And these are defined as we multiply them to get the number 1, which is the multiplicative identity. So examples of reciprocals would be like 3 and 1/3, because if I do 3 times 1/3, okay, multiplying my fractions, I'd go straight across. 3 times 1 is 3, and 1 times 3, and we get a 1. Or if I had, say, the number -11, and I flipped it over, -1/11, and when I multiply those, a negative times a negative would give me a positive, and -11 over positive 11 over 11 would give me 1. So reciprocals are when you flip them. It's a little bit easier to see with fractions, like straight up fractions. So 2/3 and 3/2, when you multiply those together, you get 6 over 6, which is 1. So opposites are when we are just changing the sign. Reciprocals are when we flip them over. And when we deal with like perpendicular lines, you have to do both. And so they're called like opposite reciprocals. So you want to make sure that you know the word opposite, you know the word reciprocal. I will not ask you about the words additive inverse or multiplicative inverse. I just want you to file those away in your brain somewhere. Now, last little piece of content here are the actual properties. Okay, so now that we've talked about the different types of numbers, we're going to talk about their properties. And by that, what we mean is how these numbers behave. What do they do? A, B, oh, I shouldn't do that. A, B, and C are real numbers. Okay, and we've defined what real numbers are. I don't think any of these properties are going to be new to you. I think they're all going to be review, but they are absolutely like crazy critical that you know what they are, even if you don't always know the word that goes with them. First property is something called closure. If you think of something that's closed, if our classroom is closed, if the door's closed, the windows are closed, everything that happens in the room stays in the room. And so by closure, what we mean is this. If I take two numbers that are real and I add them together, I will get another real number. And if I take two numbers that are real and I multiply them, I will get another real number. It's like staying in that big Venn diagram that we had way back here. As long as I operate on numbers that are inside this big real box, then the result will stay in that box. I'm not going to take two real numbers, add them together, and get something that's imaginary. Okay, that's actually very straightforward. Second property, and you'll have heard of this, commutative. Okay, commutativity of numbers. When I taught middle school, I would have students actually walk around the room to illustrate this. But this is what commutativity means. It means A plus B is the same as B plus A. In other words, 2 plus 3 is the same as 3 plus 2. It also works with multiplication. Okay, so 2 times 3 is the same as 3 times 2. It does not work with subtraction or division. And so we would say adding is commutative and multiplying is commutative, but not division and not subtraction. 2 minus 3 is not the same as 3 minus 2. So commutativity works for adding and multiplying. This is where it comes up in algebra classes. If you are factoring, and you get this will probably bring back some nightmares from Algebra 1. One student gets this, and another student gets this, and somebody will ask the question, they'll raise their hand and say, Miss Taylor, I got x plus 2, x plus 1 instead. Is that the same? Yes. And the reason is multiplication is commutative. You can multiply those parentheses in any order that you want. Third property is the associative property. This has to do with grouping. So if you think of like, who are your associates here at school? Your associates are your group. And this is what associativity means. If you're adding a bunch of numbers, you can add the first two and then add the third one in, or you could add the second two and then add the first one in. So you can regroup, and it also works with multiplication. That actually allows us to do some pretty interesting things that you probably do without even thinking that you're doing them. So if I asked you to add like 1 plus 3 plus 9, you might do this. You might say, ooh, 1 plus 9 is 10. And then 10 plus 3 is 13, rather than doing 1 plus 3 is 4 and 4 plus 9 is 13. It's easier to group them. And what you're doing when you do that is you're using commutativity to switch the order, and then you're using associativity, and it allows you to kind of regroup and solve the problem or simplify the problem in a different way. So that's your commutative and your associative come into play anytime you do that. So that's your associativity or your grouping. Fourth one is the identity property. And I threw out these words a little bit earlier. This means like that A plus 0 is equal to A. In other words, if you add 0 to any number, it doesn't change the number. And you can also do the same thing with multiplying by a 1. 0 is called the additive identity and 1 is called the multiplicative identity. That should be pretty straightforward. So any number here, like 3 plus 0 is 3, or 1 times 3 is 3. This actually is really, really important. And I'm going to put property 5 with it, which is the inverse property. And this ties into what we were talking about earlier. If you take additive inverses or opposites, A and negative A, and you add them together, you're going to get that additive identity 0. And if I take reciprocals, I will get the number 1. And so if I take A times 1 over A, that would give me 1 over A, or A over A, which is 1. And it ties into that. It's like dividing both sides by an A there. Now, take a moment, pause the video, and just think about these for a moment. Make sure that like you understand like 0 and 1 are really, really important. And then I'm going to add a little bit to the notes here. All right, so what am I writing here? Very important for solving equations. We do so much equation solving in algebra, and most of your reasoning for why you do what you do comes down to these two steps. So for instance, if I were to give you this equation and you were to tell me subtract 3 from both sides, and I were to ask you why are you subtracting 3 from both sides? The answer to that is the additive inverses give us 0, and 2x plus 0 gives us just the 2x. And so you're using this to determine what you want to do, and then once you have the 0, that's what allows you to isolate the 2x. So they come in super, super useful. Last property is distribution, or the distributive property. And this is the one where you multiply over parentheses. When I taught middle school, I would have students kind of discover this or figure it out on their own. A lot of times people will put in like little arrows here. You don't have to put the arrows in. If I put the arrows in, it's just to illustrate what I'm doing. Sometimes I'll have students put the arrows in and then they don't do the multiplying. So what this is saying is that when you have something multiplying a group, it multiplies everything in the group. And we could look at this and just kind of see that it works. If I follow order of operations, I would add first. And then over here, following order of operations, that's a plus sign. I would multiply, and multiply 2 times 4 is 8, and 2 plus 6 is 8. And so you can see that they're the same. And you can plug in any numbers you want. You can put in some negative numbers, some decimals, some fractions. You probably don't want them, but you could plug it in and you could see that works. Now, sometimes 0 will do some funky things with some of these properties, like you can't take the reciprocal of 0 in here with your inverse property and so forth. So that wraps up our first lesson. Take a second if you need to. This video is going to be posted online, so you can go back and rewatch it. You can go back and supplement your notes, write down any definitions that you have, and then I will post what your homework is, and we'll have another day to kind of talk over this and and emphasize what these properties are. Hopefully they are familiar to you. You've seen these words before, you've used these properties, but I can't emphasize enough how important they are. And if you've struggled in the past with solving equations and figuring out what you need to do, it's all going to come back to these properties. So my goal for you guys is when we start solving equations, it's going to seem easy and make sense because you know the properties. All right, that's a wrap on our first Algebra 2 lesson.